Yeah, hello everyone. Welcome to my talk. Today I'll be presenting our work, which is a fault attack on side channel secure lattice-based key encapsulation mechanisms. So I'll begin with the state of the art of post-quantum cryptography. That is like NIST has been selected some algorithms for key encapsulation mechanisms and digital signatures, and they have published their first draft very recently. And they have selected Crystal's Kyber as which is a lattice-based key encapsulation mechanism as a key encapsulation mechanism and for public key encryption. Now, the standard has been selected. Now, these algorithms will be deployed in real-world cryptography applications. So this is high time. So we consider about side channel security, like the security for implementation of these algorithms. And side channel attack is a very potent attack against cryptographic implementations, which uses like some physical information such as power consumption or electromagnetic radiations from the device, which executes the cryptographic algorithm. And they use, adversary uses this information to break the cryptographic algorithm, which is mathematically secure. So, and for all the cryptographic all the post-quantum cryptographic algorithms, there has been several side channel attacks has been shown before. Now, as the attacks has been shown, countermeasures comes into place too. And masking is a probably and more popular countermeasure which has been integrated for post-quantum cryptographic algorithm, especially lattice-based one as well. And I'll not go too much details of masking. I'll just give the brief idea here. Like if this is a cryptographic algorithm, then and S is the secret in the cryptographic algorithm, then side channel attack can break that algorithm. However, in masking, we split the secret or any secret dependent data into multiple shares and operate all the, and use all apply all the operations on these secret shares as like the previous version. But those secret shares doesn't have any like dependencies, but combination of those secret share will be the actual secret. And the previous side channel attack will not be possible here. And yeah, higher order attacks still possible, but with higher order masking, it's still preventable. Now, how we use like which algorithms of the key encapsulation mechanism Kyber is more vulnerable? That is the decapsulation algorithm that has that uses the long-term secret key. Like this secret key will be used multiple times, and this that's why most of the researcher, the favorite part of the researcher was the decapsulation algorithm. They have masked them very in several works and tried to make it as cheap as possible cycle-wise. So this algorithm has like three parts. First part, it decrypts the message from the public ciphertext. Then it computes the re-encryption and then checks this re-encrypted ciphertext with the previous public ciphertext. And if it is like the same, then it will give away the valid shared key, otherwise invalid one. Now, this is the normal decapsulation algorithm. And with masking, it becomes, and it has several operations which are arithmetic operations like these ones, and there are several operations which are Boolean operations like XOF, which uses the k-check one, and that is Boolean operation or bitwise operation. So to mask these components, we require two kinds of masking techniques. One is arithmetic masking, which is used in arithmetic operations, and Boolean masking, which are used for Boolean operations, such as that secure and or k-check for k-check and all the equality check those. And the relation between like what is arithmetic masking? The that is like for arithmetic and Boolean masking, everything is same. For both, we need to split into shares, but the relation between shares and the unmasked value is different. For arithmetic, it is like summation of these shares is the unmasked value. For Boolean masking, it's the XOR of the shares. Now, as we need two kind of masking techniques, we need some conversion in some time. And we need arithmetic to Boolean conversion and Boolean to arithmetic conversion, both conversions. And it becomes, the previously shown decapsulation algorithm becomes like this. Now we have several more components due to masking, and such as these are the components which wasn't there before using masking, but now it comes into place. And the goal of this work was like, there are several attacks has been proposed for side channel attacks and also fault attacks. Now, we know some fault attacks, we know some of the countermeasure of the fault attacks, but which components are included due to masking, those are not yet verified. Like those can handle those new, different kind of attacks or not. They can surely handle side channel attacks in most cases, but not other attacks. Those hasn't been checked. So the goal of this work was like, real world adversary will not be limited by side channel attacks. They might perform other attacks such as fault attacks and also some other attacks. Like now, here our goal was to like the added components for the side channel to protect against side channel attacks. Are those secured against fault attacks or not? And vice versa. But here we observed that it is indeed not secure, and cross attack, which is like fault attack on side channel secure implementation, is possible for Kyber or any lattice-based or learning with error-based key encapsulation mechanisms. Now, I'll just only give Kyber as an example of that. And this is the decapsulation algorithm of Kyber algorithm, decapsulation operation of the Kyber algorithm. And we actually found the vulnerability in this compress operation. The position has been shown here, this one. And this compress operation basically uses the arithmetic-to-Boolean conversion algorithm. And this is the algorithm, compress operation in more details. The compress operation, what it does, it takes two arithmetic shares and then performs some operation. It changes the field from a prime modulus to power of 2 modulus, and then it performs arithmetic to Boolean conversion, and finally it extracts the most significant bit shares. So it has few lines here, I know, but we are gonna focus on this arithmetic to Boolean conversion. I'll simply just like line out the idea of the attack with a very simple example. Like here it is like power of 2 to the power 13th ring has been taken, but I simplified it to 2 to the power 3 only. Now this is the A to B conversion algorithm, and x0, x1 is the input, and c0, c1 is the Boolean shares of the output of this algorithm. Now we will be using fault attack, as I mentioned, and we have used stuck at one fault. We give this fault at x0, 0 position, and that fault will be active only if x0, like the 0th bit of that x0 share, if it is 0, right? And that fault will always propagate to the least significant bit of the output. But what about the higher bits? That is also possible to propagate through carry, only if the unmasked value of x0, the 0th position of x value is 1. And for further calculation, please, you may check that if it's correct. But our target is like to get the most significant bit out, because we were doing like the compress operation, and that gives out the MSB. So we want the carry to propagate to C2 here. And that is only possible if the similar result, by using the similar technique, it's verifiable that it only happens if x0, the 0th bit of x is 1, and first bit of x is as well 1 in this calculation. Then only the MSB will be faulted. It's possible to fault it if all those conditions are satisfied. And yeah, these are some conditions, and these results can be very easily translated to the Kyber case, the original case where we had 2 to the power 13 ring and we shifted to 2 to the power 3. Now this result only be translated when we induce the Staccaton fault at the x10th position. Then it will go towards x12 by following the previous example. And then also the message will be different with the similar condition. Now it becomes like x10 need to be, like 10th bit of x need to be 1 and 11th bit of x need to be 1. Now if the message is different, that means the decryption failure will happen where the actual Kyber was checking like the ciphertext, regenerated ciphertext and the previous ciphertext was same or not. If it is, that is like from the result, it can be detected what is the input value of x from the output. So, and decryption success, like the effect of fault will not be seen if the other results comes. Like the 10th bit of x is 0, but it only happens with certain probability, as we are faulting just only one shares instead of the unmasked value. So as we don't get it with probability 1, we have to repeat the experiment several times to get to increase the probability of our knowledge about the unmasked of the input value x. And after that, we will use these results, like decryption failure will give us such equation, first equation, and decryption success will give us the second equation. And by we can rewrite this equation in the following manner, and then by solving these inequalities, we will get away the secret and error. S is the secret and E is the error. But getting 1 is enough for us. And we have used the Geron-Delvaux inequality solver to solve these inequalities and get the secret. But we faced a problem here. The decryption failure cases we observed, that is 97% cases. And the decryption success is only for 3% cases. So it has a very big problem as it's not balanced at all. So, and this inequality solver uses Belief propagation to solve it, to converge the result to the exact secret. But with this kind of unbalanced inequalities, it is not able to converge. So we had to reject some samples. As we have 97% cases for decryption failure, we plan to reject those, and with that, it becomes balanced and solvable. But another problem comes into place. That is, like in ideal case, we consider that we'll be like successful to induce fault in 100% cases. But in practice, it's not the case. We were just able to succeed with this kind of fault as only in 10% cases. Like we were able to fault x, the 10th bit of x0 shares, only 10% cases. And in 90% cases, we have observed fault, multi-bit fault from x0 to x7, like last 8 bits. However, the good news is these faults doesn't give us any information, but these faults are not able to propagate towards the x010 so that we don't get wrong results most of the time. So these are noise, but these are removable noise for us. So although that doesn't increase any signal, but it doesn't cause any misinformation. Now, as a result, we required like 35K inequalities, And we get that by using 70K different ciphertexts for decapsulation algorithm. And maximum time we had to repeat. The repetition was needed for to make it balance. That was like 180 cases for decryption success. But we, like on an average, we just had to repeat it like 20 times, not more than that. So total fault, we required 1.9 million. That is feasible on M4 board. And this is the setup we have used to induce fault. This setup actually shows the H-field probe, how we use it on the discovery board, STM32F4 discovery board. And yeah, we have used Kyber 512 algorithm for that. Now, what is the takeaway here? We show a fault attack on side channel protected implementation of Kyber. And this is not really limited to Kyber. It can be extended to any LWE-based schemes or any variant of LWE-based schemes such as Saber. We have shown that result in our paper. Please go there if you like. But it can also be applied to NeHope or any new schemes which came very recently, such as MAG or any other this kind of schemes. And this can also be applied for higher order masking. We have shown just for first order masking, but it can be applied for higher order masking with same number of fault. Fault number will not increase at all. But the time of execution will increase as higher order masked implementation takes more time. So yeah, and we have shown that with 10% signal, 1.9 million fault can break the Kyber 512 algorithm. So what we need for future, that is countermeasure of such attacks and exploration of this kind of attacks for the Kyber or all the selected algorithms which will be deployed later. And we need combined countermeasures so that we can prevent against side channel and fault and all these kind of physical attacks which are possible. Thank you. And now I'm happy to take any question.